self-assembly, self-repair, self-reconfiguration for deployment in hazardous environments such as rescue missions or space exploration. And today she will talk about the modular robotics systems. Welcome, Reem.
Hello, everybody. Well, it's going to be hard for me to stand still in one area. I usually like to move, but I'm going to try. So thank you very much for being here today. I would like to start by thanking Dean Soap. He's the supervisor for this research project. And I would also like to thank Professor Janie Pallas in the back. Thank you, Professor Pallas, for your unlimited support. So my name is Reem, and today I'm going to talk about modular robotic systems. So this is our agenda for today. We're going to start by discussing modularity, self-assembly, self-reconfiguration, self-repair, self-reproduction, evolutionary robotics, printable robots, and finally, automatic manufacturing. So what are modular robotic systems? They are robots that are composed of smaller units called modules. That's why we call them modular robots. And the goal of building such systems is to have versatile systems, robust systems, and low-cost system. What do I mean by that? Versatility allows robots to change their form, change their shape, and change the way they can locomote or move accordingly. That's cool, right? Yay! Come on, people! Robustness. Each modular robot will carry redundant modules in order to self-repair. So if it has like a problem or a failure, it can repair itself. Yay! And low cost, because nowadays everybody is talking about 3D printing systems. And also on top of 3D printing systems, once you produce a lot of identical modules, the cost of producing a certain module will go down. Is that right or wrong? Where are my economic people? Yeah, that's right, cool. So modularity, each module is a small computer. It involves actuators, sensors, computational and communicational capabilities. Why? We will know soon. So modularity allows robots for self-assembly, self-reconfiguration, and self-repair. What do I mean by that? Self-assembly, if I have multiple modules, they can communicate with each other in order to connect, attach to one another, and form a bigger and more complex robots accordingly. Why do we need that? We need it in remote environments exploration, hazard and dangerous environments exploration. Like if you have an area where a lot of earthquakes happening, or like a war zone or something, or where a bomb happened and the robot was split into multiple modules. These modules still can communicate and self-assemble a bigger robot, a better robot, a stronger robot that can perform more complex tasks. Self-reconfiguration, on another hand, allows robots to form different shapes. So you can start by having a robot that has 2 legs, a biped robot that can walk, and then it can change its shape to a wheel. And it can change its shape as well to a worm. Let me take this. Oh, it has a cable. I can't take it. All right, so we're gonna stay here. So let's assume that we have an unstructured. I can take it out?
No. You can.
Oh, I can.
Without mic.
Where's the mic? Can you guys hear me?
Yeah.
Perfect. That's better. I really can't stand still. So let's assume that we're having an unstructured environment. Give me some examples of unstructured environments. Yeah.
A volcano.
Volcano. Moon. Mars. What else? Space in general. Sorry?
War zone.
War zone. Excellent. So you can have a robot. Let's assume that we have a wheeled robot. And then this robot saw a tunnel. What it's going to do? It's going to change its shape to a worm, and then it's going to go through the tunnel. Okay, I've gone through the tunnel, now what am I going to do? I'm going to change my shape, let's assume, to a biped robot. Then I'm going to walk and do a different task accordingly. So we have different classes of self-reconfiguration robots. We have lattice, we have chain, we have mobile. In the first one, lattice, we have a pattern or a 3D grid that guides the modules accordingly. So the modules know where to go, depends or based on these grids. In a chain class, we have a tree topology. Anyone from computer science department here? Computer science? Computer engineering? Are you familiar with tree topology, chain topology?
Not yet.
Okay, not yet. Okay, soon. Okay, you will be familiar with these soon. Unfortunately, there's no time to talk in details about these topologies, but let me tell you about the mobile class. The mobile class, each module will detach itself from the robot and maneuver independently to find the new location and attach itself. Is that cool? Yeah, it's all right. It's hard. It is so hard. That's why we don't have a lot of research done in this area. But I'm encouraging the undergrad students and also grad students to do more research, yay, of course, in this area. Self-repair. Again, modular robotic systems carry redundant modules. Let me actually explain the difference between homogeneous and heterogeneous modular robotic systems. So if all the modules are identical, we call this robot a homogeneous modular robotic system. If we have different modules, what do we call it? Heterogeneous. Yay, heterogeneous, cool. So each modular robotic system will carry redundant modules. Why? Because if there is a failure, the robot needs to know which module has the deficiency, eject this module, and replace it with a fresh one. Awesome? Yay, cool. Self-reproduction. Okay, this is crazy. I don't want to play a video because it's going to be underwhelming. Now I'm going to tell you about the concept. So a self-reproduction robot can destroy itself and build itself to form the same shape it had before. Is it cool?
What you were talking before?
It is similar. The other one is self-assembly. That's a good actually point, because this one is a generalization over self-assembly. That's a great point. People, differentiate between this and self-assembly because, it should build the same identical robot or previous robot. That's why we call it self-replicator. Close enough. There are a lot of similarities actually between these different types. So let's talk more about applications. Now you will see that point. Each robot can perform various applications because it's similar. It's all interdependent. So CE-Bot, this one was the first modular robot system that was implemented in 1990. Probably it's older than some of our audience in this room. Not here. This one was actually implemented by Fukuda and Kawauchi in California. This robot here, they didn't call it actually modular robotic system, they called it cellular because they did not call the pieces or units modules, they called it cells. These cells are capable of self-assembly and self-repair. Next we have, this is cool, Polybot. Polybot is the first self-reconfigurable robot that was implemented physically and it demonstrated self-reconfiguration. It actually has 3 generations. This is the first generation here. The second generation, I use the laser. The second generation has electromechanical latches to enhance the attachment to other modules. And the third one here is smaller because it lacks DC motor. Just to keep it smaller. This robot here, what it looks like?
A wheel.
A wheel, yeah, it looks like a wheel. So this robot still reconfigured to a worm. How easy it was? It detached one end and then it was a worm. The hard part is the locomotion part. How can these modules move like a wheel and then, figure out, no, now I have a different shape. So now I need to change my locomotion mode to move like a worm. This is difficult, guys. Crystalline. Crystalline was implemented in Dartmouth College, and I think it moved to MIT by Professor Russ. The modules are called atoms, and each module is capable of contraction and expansion. Does it remind you of anything? Bicep, yeah, yes, what else? Generalize it. Muscles, yes. So it was inspired by the muscles. It contracts and expands, as you can see here. But it has a small problem. The single module cannot move. You should have a minimum of 2 modules connected to each other in order to have a movement, like an acceptable form of movement. That's why we have now, not telecubes, I'm going to jump telecubes, skip it, M-tran. What do you see here? What is the difference here? Each module has, they're looking at you, they're waiting for you to answer. Just shout out anything that comes to your mind. 2? Yay! Each module has 2 submodules. The problem we had here is that each module is composed of like a solo module, a solo one. So it can't move on its own. But when we have 2 modules connected to each other, now these modules can move, can crawl. Of course, if you have 2 modules connected to each other, it's going to give you a better way of movement or locomotion. But still, 1 is good enough. And today we're having Ditto. That was actually implemented in 2017, last year. And everybody's saying like 2018 is still 2017, whatever. The difference between this one and this, it was inspired by M-tran. The difference here is that these cases are 3D printed. So you can download the design and 3D print it either here at UB or maybe in like, if you're a member of a meetup group that has a 3D printer, you can go and 3D print a case. And you can go to eBay and buy the electronics and assemble the module yourself. Okay, let me show you a video of Ditto before moving on.
This is Ditto. Ditto can move by itself. And it can even turn around. It doesn't look like much, but when it links up with the rest of its parts, things get a little bit more interesting.
That's self-assembly. presentation. I hope you guys liked the video.
Yeah.
Hey, cool! So we talked about 3D printing to print the cases of robots. You saw the cases of Ditto. I think it was cool, but it's not as cool as these robots here, where 3D printed was used to create origami-inspired robots. Anyone is familiar with origami, playing with papers? Yay, cool. So you can actually grow this hobby and build robots with it. Use 3D printing to print the case and then attach the electronic part using either Arduino, Raspberry Pi. Anybody is familiar with these boards?
Raspberry Pi.
Awesome, cool, cool, cool. To build your own robot. So that's really cool. Now the exciting part, evolutionary robots. So we talked about hardware, modular robots, the locomotion mode, but still you need a brain in each robot in order to perform these locomotion modes, in order to figure out where to self-assemble, how to self-reconfigure, and how to do also self-repair. So we're using evolutionary algorithms or evolutionary computation in order to evolve the brain of the robot. Here we're seeing a robot that looks like a sheep, maybe, a dog, with 6 legs. I have no idea. So the researchers, Zykov and his team, they used evolutionary computation to evolve the brain of this robot and allow this robot to leave a cage. They put the robot in a cage, they opened the door, they did not program the brain to figure out how to leave the cage. No, they used evolutionary algorithms, so the robot will know how to leave the cage once the door is open. Did it leave the cage? Any guesses? Yeah, okay, yeah, just say it with confidence, yes. And they measured the distance by tracking this red ball in here. So what are we doing here at University of Bridgeport? And now the godfather of evolutionary and modular robotic systems, Professor Soap, is here. Thank you for being a supervisor for this cool project. So my PhD research is developing an autonomous designer for modular robotic systems. So instead of having a person who designs and thinks, oh my God, okay, this new robot, how it should look like, we're building a system that should design these modular robotic systems automatically, autonomously for us. We just give the system as input the shape of the module, the number of modules we have, and the task to be accomplished by this robot, and the system will give us these resulting cool robots. So in conclusion, we learned today about modular robotic systems, how to build the brain, and how to design modular robotic systems using evolutionary computation, and 3D printing, and what else?